The previous video used the normal distribution for hypothesis testing. Now we want to do something similar for confidence intervals. Again, these techniques tend to be specific to the type of statistic, so we will still be talking about a difference in proportions. I'll use the same data as last time. Here are the details. Recall this was a psychology experiment about two ways of asking a purchasing question. This is a controlled trial. There is a control group and a treatment group, and each group has a percentage of buying and not buying. Here was the data, which showed that more people in the treatment group chose not to purchase. And here was the sample statistic, showing a difference of 20 percentage points between the two proportions. An analysis in the last video showed that this difference was statistically significant. But now we want a confidence interval. What does that mean? Well, let me remind you. It means that around this 20 percentage points difference, we want to know where the population parameter is. That population parameter is still a difference in proportions, but it is an unknown difference in proportions. We think this opportunity cost reminder does affect people's decision making, but we don't know by how much. The sample statistic gives us a starting point. We want to know where the population parameter is likely to be, and that's in a range around the sample statistic, a confidence range. This might be pretty close. We might be 95% confident that the population parameter is between 0.19 and 0.21. It might be very, very precise, between 0.199 and 0.201. It might be less precise, between 0.15 and 0.25. And it might be quite wide, between 0 and 0.4, including the possibility that there is no difference at all. A few videos ago, we used bootstrapping to make random samples, looking at the distribution of those new samples and taking the middle 95%, excluding the top and bottom 2.5%, to get the 95% confidence interval, or something similar for other percentages of confidence. Now I want to show you how to do this using the mathematics of probability theory. First, let me remind you about the sampling distribution. Our random process, both for the shuffles and hypothesis testing and the bootstrapping in confidence intervals, involves making a bunch of randomly generated samples. Then, from each randomly generated sample, we calculate the relevant statistic, which is the difference in proportions. That gives us a bunch of statistics. Then we treat all of those statistics as a new distribution, the sampling distribution. It shows all the possibilities of what the population parameter might be using all these random samples. The central limit theorem, which is the key idea for this section, says that under certain reasonable conditions, the sampling distribution is normal. This makes all the mathematics here work. We can work with the normal distribution and its properties. So, let me show you how to calculate the confidence interval. Say we are aiming for 95% confidence. The sample distribution shows all the random samples. I've labeled the x-axis here by standard deviations away from the mean, out to -3 and +3. Again, remember that almost all of the normal distribution falls within 3 standard deviations. I want to know what is within 95% of the possibility. Where is 95% of the data? Well, it's in this range, between these two bars. The excluded tails here are 2.5% of the data on either side, and removing them does give you exactly 95% of the data, of the sampling distribution. The range in terms of standard deviations for 95% of the data is approximately -1.96 standard deviations up to 1.96 standard deviations. Like going from z-scores to percentiles, there is a complicated function behind this that goes from the 95% to the 1.96, but we're not going to go into the details. The ranges for confidence will just be given to you, or we'll use R to calculate them. So we have this range in terms of standard deviations. To apply this, I need the mean and standard deviation of some distribution, and once I have that, I can calculate the 95% confidence interval. It starts at 1.96 standard deviations below the mean, which is mu minus 1.96 times sigma, and then it ends at 1.96 standard deviations above, which is mu plus 1.96 times sigma. That's the process. Let me apply this to the data for the psychology study. The mean of the sample distribution is the sample statistic, 0.2. The standard deviation, which for the sampling distribution is often called the standard error, is 0.076, We calculated this in the last video, so feel free to review the process from that video for where this 0.076 came from. Well, then I apply my new setup. I take 0.2 minus 1.96 times 0.076, and that gives me 0.051. And likewise, I say take 0.2 plus 1.96 times 0.076, and that gives me 0.349. This is my 95% confidence interval for the population parameter. Let me recap. We have a sample statistic. That sample statistic becomes the mean of the sampling distribution. The central limit theorem says that the sampling distribution is normal, again under some reasonable conditions. We calculate the standard deviation, also called the standard error, using the formula from the previous video. Then, for each standard of confidence, there is a confidence interval defined in terms of standard deviations. We use that and the mean in the standard error we just calculated to calculate the confidence interval. No randomization required, just the central limit theorem and the tools of mathematical probability. This distribution is what we would have produced if we did many, many randomizations. It is reliable. The probability theory says so definitively. This is what bootstrapping would have produced with many, many randomizations. We can be 95% confident that, in the population as a whole, the effect of reminding a buyer about the opportunity cost means an actual difference in the purchase rates, and that difference is between 5.1 and 34.9 percentage points. In particular, 0 is not in the range, so we can be 95% confident that there must be at least some difference, and this matches the previous video, which concluded that the sample statistic was indeed statistically significant, and the null hypothesis could be rejected.